business growth. So Lalamove is a 24/7 founded in Hong Kong in 2013, and our markets cover 13. Our services cover 13 markets and over 400 cities globally, including Asia, Latin. Corporation can access wider fleet of driver vehicle operated by our professional driver partners. And in last year, our Lalamove achieved the world's largest logistic transaction platform with 1.4 million of active drivers and over 15 million monthly active users. So what is the real-time data processing and how it can boost our company? Let's imagine several scenarios. Imagine you are browsing products on a online shopping platform, and the products you are interested in keep popping up to catch your eyes, to motivate you to place more orders. Or imagine you are a platform engineer you have to manage thousands of processing jobs, and you can always get the alerts immediately when there's any abnormal job, and you can take action as quick as possible to mitigate the impact. And also, you can imagine you are a data analytics, and you are working with a dashboard that can update in real time so that you can generate insights and take marketing strategy as fast as possible to gain the time to market advantage. For Lalamove as an instance, the logistic environment is dynamic. It is affected by several factors like the weather condition, the distribution of driver and users, or the seasonal events, etc. We have to consider all these factors into account to generate the best marketing strategy to fulfill our users' satisfaction. However, if we process this data in offline manner, for example, we wait a complete set of data from last day and processing them in a batch. In some aspect, this data are actually losing some values. For example, if there are a lot of delivery codes from users, but there's a fewer drivers but there's a fewer orders were actually placed, or if there are a lot of orders were placed, but there's a fewer drivers responding to these orders. If we processing those data into a into batch way, we cannot make a marketing strategy in time in order to, so we will losing some opportunity to satisfy our users' need. And that's why it's important to have a real-time analytics. So how we do this real-time analytics? Especially we consider a large scale of business, which can generate terabytes of data every day. There's any tool that can help us to is scalable to handle any volumes of data. Is fault tolerance to ensure the data is reliable and is reliable, and also is it high available to ensure the data is always fresh, and we can base on this fresh data to make our decision. Also, is it easy to use and even open source? The Apache Flink is the answer to all these questions. So here is the typical example of how we use Apache Flink to process data from end to end. Starting from the we first step is to collect the data from various data source. We can collect data from message queue like Apache Kafka, or we can collect data from relational database like MySQL, or we can also collect data from file or even API requests. After we collect this data, we can start to process this data by using the Apache Flink. We typically use it for to do the data standardization before we moving this data into data warehouse. And also we can enrich the data from various data source. It's kind of like you are doing SQL joining in a relational database, but this is joining the data from various data source. And we can also do some aggregation for analytical purpose. After we process this data, we can move this data into data warehouse. The Apache Hive is one of the traditional data warehouse in big data field. Also, we can also move this data to analytical database like Apache Doris. Also, we can move it back to MySQL. Actually, we can move this process data to everywhere. And after we store this data, we can have some data application, like we can create dashboard to visualize our data. We could, based on this data, to do some anomaly detection. We could also feed this data into machine learning model to train our model. Yeah. So our streaming platform is the one-stop place for our users, our data warehouse engineer to process their data using Apache Flink. Our platform is managing over 500 computing units with over 8,000 virtual core during peak season. And there's over 8,000 of tasks running every day. And by leveraging the Apache Flink, we can process massive amount of data in low latency and high processing throughput. And here are some typical use case for our users. The first case is the real-time data analytic. Our data warehouse engineer can develop the data pipelines for the real-time dashboard, so that our management team and business intelligence can, based on this data, to analyze our daily business performance or even making some marketing strategy. And for the second use case is the real-time decision making, strategy decision making. For example, we have a pipeline to calculate the dynamic surcharge for a driver For example, when there's a low response rate, there's a lot of order place, but lower drivers are responding to our orders, that we can adjust as an incentive to attract more drivers to take more orders. And the third use case is the real-time data monitoring. For example, we have to monitor the behavior of our users and driver in order to do some anomaly detection, like we detect are there any fake orders. And when we detect these orders, we can send out warning to our correspondent team to take further investigation. And here is the platform architecture. We starting from the bottom. Our platform are built on top of hybrid cloud service provider, including AWS and Azure. And we can schedule our Flink job into two different resources clusters, including the traditional one, the Hadoop Yarn, and the newly cloud native one, Kubernetes. For the engine layer, we provide a customized Flink code to enhance our users' they can develop Flink job more easily. And also we provide richer connectors that's not provided by the community. And also we support multi-version deployment so that our user don't need to afraid to always to upgrade their Flink jobs. And for task development, we provide our users can submit either SQL or Java tasks to process their data. And we also provide data lineage capabilities so that our users can diagnose their complex data flow. And they can also upload their UDF, which means the user-defined function. They can implement their own functions to for their custom business need. And for the task operation, we also provide a monitoring, logging, data task governance, and even autopilot capability to ensure our data pipeline is as stable and is cost effective. So let me invite my colleague Jenny to share how we actually leverage the cloud native technology to build our platform. Thank you. Thank you.
Okay, let me talk about how we started our cloud native journey. Firstly, why we migrated from physical EC2 machines to Kubernetes. The first reason is Kubernetes has provided scalability. It's easier to scale nodes in and out compared to traditional EC2 machines. And secondly, it provides more stability. It can replace the abnormal nodes in just 5 minutes. And compared to the traditional EC2 machines, it would take nearly 10 minutes. And thirdly is isolation. It can a resource-intensive application in one node, one pod will not impact the performance on the other pod. So it can prevent the interfering between the Flink applications. And since we decided to migrate to cloud native, the first step is to deploy our Flink application in a cloud native way. So basically, we utilize Flink Kubernetes operator. And Flink Kubernetes operator we think is the best way to deploy a stateful application. It is running in a control loop, and it keeps monitoring the life cycle of the Flink deployment. And we also develop a functionality to synchronize the status to our platform's backend. And we also developed the customized matrix reporter to report the matrix of Flink job to our company's monitoring platform. And even though we have deployed to Kubernetes, we have running in a cloud-native way, we still face a lot of challenges. The first one is there's increasingly cluster scale due to our business growth. As Lalamove has expanding to new markets and new business lines, more and more tasks are running on our clusters. Sorry. And secondly, due to the rapid development cycle of our Kubernetes and Flink, we need to do the rolling update to our applications regularly. And handling these thousands of tasks has deeply increased our maintenance cost. So we think about to develop an autopilot to help us reduce the maintenance cost. Firstly, as we have mentioned before, Flink has the capability to handle real-time data and can do real-time monitoring. So we basically utilize Flink as our rule engine. By leveraging the multiple connectors like Kafka, HTTP connectors, and MySQL connectors, we have collected matrix from various sources like CPU usage, memory usage. And then the Flink job will constantly monitoring if the matrix has met the rule we have predefined. If it does, then the Flink job will call an HTTP request through the customized HTTP sync we have developed to perform some actions like adjusting the parallelism or adjusting the memory of the task running on the clusters. And this autopilot has bring us a lot of benefit. The first one is reducing our maintenance cost. For example, when we need to when we need to upgrade our Kubernetes version, we choose to do blue-green cluster migration. That means we need to stop thousands of tasks on the existing cluster and then restart them in the new one. So if we do it manually, we need to do it 1,000 times. But with autopilot, we just need to configure a simple rule, and then it will automatically help us to restart the jobs from, restore the job from the old cluster to the new one, and in a very safe way. And secondly, autopilot also benefit our stability. It will proactively detect if there's any abnormal Flink job, and we recover it. And sometimes we will develop some new features on our Flink engines, and Flink sometimes will introduce some new optimizations. And autopilot will orchestrate the seamless rolling update for the outdated Flink job to the updated version. And the most important one is autopilot can help us to do cost saving. And if you take a look at this graph here, this is the resource consumption of our task. It goes up during the peak hour and during the day, and it goes down during the nighttime. So if we statically allocated resource for our task, there will lead to resource waste. But if we dynamically allocated resource for the applications, there will be potential to be cost effective. And you may be curious why we need to develop our own autopilot application, since there's already open source Flink autoscaler and HPA. That's because we offer more capabilities. The first one is we have a predefined operational windowing, because we allow only the adjusting the resource only during the non-peak hours. If you take a look at this graph, the red arrow indicates the decreasing request of the CPU resources during the non-peak hour. And the green one shows that the CPU request is increasing before the peak hour, that is about 6 a.m. And we're doing this because we need to make sure that our Flink application have the enough resource to handle the peak traffic during the peak hours. And Autopilot also can prioritize the scaling target. We can configure the auto scaling rules to only scale our low priority jobs, and it will not impact the high priority ones. And since we have scaling down our task, and the whole cluster usage has went down, we still find out the fact that we could not scale down our machines. Why? Because of the resource fragments. If you take a look at this graph here, we are currently, our cluster is using the least request policy. And it is also the default policy of Kubernetes scheduler. And the Flink pod will be evenly distributed through the nodes, because the default scheduler will always find a node with low utilization to fit in. And then we discover the beam-path policy. The beam-path policy will schedule the pod on the high usage nodes with enough resource. And the whole cluster will be more beam-path. And obviously with 6 parallelism, you will see that a beam-path policy will use fewer node than the least request policy. And even if we have used beam-path policy, we found out that there's still some scenarios that we can't scaling down our nodes. And there is some scenarios like this. And one of the reasons is the beam-path policy only work when we redeploy the task. And if we don't redeploy the task, it will not take any effect. A case is something like this. Task A, there's 2 parallelism of task A, and it's running on node 3. And only 1 parallelism for B, and is also running in node 3. And after scaling in pod A, it is running on node 2, but task B doesn't have any potential to be scaled in because there's only 1 parallelism for it. So B is not redeployed, and the whole node 3 is not decommissioned. So we need another tool, descheduler, to help us to eliminate the remaining nodes on the low utilization nodes. And the whole workflow of our descheduler is something like this. It will firstly check if it meets the scaling down criteria. For example, if it's after 8 p.m. and if the cluster usage is lower than 90%. And secondly, it will select a node with low utilization and no core tasks running on it. then it will mark the node as unready and deschedulable so that no more pod will be scheduled on the nodes. Then it will evict the pods from the nodes. And thanks to Flink's failover strategy, the Flink application will self-recovery. And then descheduler will also constantly monitoring the whole cluster and check if there's any node has been decommissioned. And it will send the notification to us when there's any node being scaling down. And thanks to what we have done, we are able to dynamically allocate resource for our task, and 20% of our machines have been scaled in during the non-peak hours. And during the Kubernetes cluster upgrade, 100% of our tasks have been migrated to the new cluster without any manual job. And our whole platform has become more stable and don't need us to firefighting during the weekend. And in summary, real-time computing has enabled us to react on business for real-time data for a live data stream. And Cloud Native has provided us the foundation for scalability and resilient. And other tools like Autopilot and Descheduler has enabled us to focus more on innovations instead of firefighting. So we hope we are providing some valuable insights about how we utilize this kind of technology like Flink and Kubernetes to solve our real-world challenges. Hope you enjoy this sharing. Thank you.
Maybe take Adam over. Adam or Jenny. Adam. Yeah, one question. Thank you. One question. When you're trying to pack the jobs into a small number of nodes like this, you're trying to maximize the utilization on a smaller number of nodes. Do you target 100% utilization for these nodes, or I'm really not a Kubernetes platform operator anymore, but I've heard that you should kind of try to keep some spare room in the nodes that, whatever background jobs are running can have enough room. So what kind of utilization do you try to target for the nodes? And do you find that if you kind of make them run too hot, you run into problems?
I think because we are targeting to reducing our machines during the non-peak hours. So we're actually targeting for 80% and 95%. So if we can actually reducing machines, then that's the good question, good percentage for us, I think. Thank you.
All right, cool. Thank you, Jenny and Owen. If you have more questions, please find them up the stage.